Hey everybody, in this next video lesson, we're going to talk about types of bonding and we're going to specifically focus in on ionic bonding. I first want to set up a little table here that has three different types of bonding that we're going to talk about: ionic, covalent, and metallic. And in this table, we're going to include the bond mechanism, or in other words, how the bond forms, and then we're also going to talk about the elements involved. Now, in the ionic bond, the bond mechanism is usually described as a loss of electrons, gain of electrons situation. Or in other words, one element donates its electrons to another element, and those two elements are then bonded by their opposite attractive forces. There's a positive ion and a negative ion, and they're attracted to each other because opposites attract. Now, in covalent, we typically talk about how the elements involved in the bonding are sharing electrons, and so that both elements have equal share over the electrons that are in the bond. And then finally, in metallic bonding, as the name would suggest, metals not just share electrons, but every element shares all of their electrons in what is known as the electron C model. Now, we're not going to talk too much about metallic bonding because it is beyond the scope of our chemistry class. We're going to stick to basically ionic and covalent bonding, but I did want to talk about metallic bonding so that you know the difference between the three. The different types of bonds can also be identified by the different elements that are involved in the type of bonding. Typically, ionic bonding occurs between a metal, which loses its electrons, and a nonmetal, which gains electrons, and those two elements then bond because of, once again, their attraction of opposite charges. So the elements involved in ionic bonding are a metal, typically, and a nonmetal, but not always. Now, with covalent bonding, the elements involved are always two nonmetals. We do not have metals in covalent bonding. Only nonmetals participate in covalent bonding. And then with metallic bonding, only metals are involved in metallic bonding. And we talked about this a little bit earlier. The mechanism is that all the metals in the sample share all of their electrons to what is known as an electron C, or think of it as a potluck, where all the metals donate all their electrons and all the metals share all the electrons. So the first thing I want to talk about is, what is the motivation of two elements to form a bond? Why do they bond? Well, everything bonds in chemistry in order to achieve the most stable state that they possibly can. Think of this as a relationship between two elements. They want to have a stable relationship, and so they're going to figure out a way to become most stable. And there's a way to determine stability, which we're going to talk about on the next slide. But why do bonds form? It has to do with achieving the most stable state. Elements alone are unstable. Individual elements do not like to be alone. They like to be paired up with another element, and they're going to seek a partner in order to achieve stability. Only a handful of elements on the periodic table are stable by themselves, and those are the noble gases. And what do we know about the noble gases that makes them so unique is that they have a full energy level, and a full energy level is stability. As I just mentioned, the noble gases on the periodic table have a full valence energy level, which makes them the most stable elements on the periodic table. All other elements, whether it be nonmetals or metals, are trying to achieve stability, and this is what is known as the octet rule. The octet rule says that all elements are trying to get 8 valence electrons in their highest energy level. In other words, they're trying to fill up their s subshells and their p subshells, because an s can hold 2 and a p can hold 6, so 2 plus 6 is 8. Only these elements on the end have 8, and so they are stable. Everything else is trying to get 8 in their highest energy level. Now remember, there's a pattern to the valence electrons on the periodic table. Like, for example, the first column all have 1 valence electron, the second column have 2. We skip the transition metals. 13th column has 3, 14 has 4, 5, 6, 7, and then of course the noble gases have 8. The octet rule, all elements want 8 valence electrons. If they don't have it, they will either share, or they will lose, or they will gain, which forms bonds in order to achieve octet. Now let's look at chlorine, for example. Chlorine has 7 valence electrons, which means it only needs 1 more to look like argon, and so it's wanting 1 electron. Now, what if you are, say, for example, potassium here, which has 1 valence electron? Now, potassium looks like it's a long way from a noble gas. In terms of valence electrons, it's 7 away, not including the transition metals, of course. But in fact, it's only 1 away, because if it loses its highest energy level electron, it will also look like argon. So potassium is looking to get rid of an electron, chlorine is looking to gain an electron, and those two would get together perfectly in order to create what we're about to talk about next, which is an ionic bond. Ionic bonding occurs when a metal with 1, 2, or 3 valence electrons looks to get rid of its outermost electrons, and it gets close to a nonmetal with maybe 5, 6, or 7 electrons, and it tries to gain some electrons. And so a metal will donate its electrons to a nonmetal in order for them both to achieve 8 valence electrons in their highest energy level. And at that point, they are oppositely charged particles. The metal is now a positive ion, which we call a cation, and the nonmetal is now a negative ion, which we call an anion. And these two particles will now ionically bond due to their opposite attraction. An ionic bond happens when oppositely charged ions, or particles, attract. Now, before we can make ionic compounds, we need to talk about how we can use the periodic table to predict the charges of the elements when they become ions. So let's take, for example, sodium right here. Sodium has 1 valence electron, and if it loses its 1 valence electron, it will become a positive ion. So the ion's charge for sodium is 1 plus. We put the number before the charge symbol when it is charged. Calcium with 2 valence electrons will lose 2 to look like argon, so it will become a 2 plus charge. And aluminum with its 3 valence electrons will become 3 plus charge ion. Now, let's take a look at oxygen, which, as you can see, oxygen has 6 valence electrons because it's in this column in the periodic table, and they're 2 away from 8. So it's wanting to gain 2 electrons, and when it does that, it will become a 2 minus charge. Fluorine, on the other hand, is only 1 away from the noble gas, and so it will want to gain an electron and become a 1 minus charge. What about sulfur? Sulfur, just like oxygen, has 6 valence electrons. So, like oxygen, it will become a 2 minus charge. And finally, xenon, as you can see, is already in the noble gas column, which means it is fully stable and will not gain a charge. If you had to put one on, you'd put a 0, but we typically don't put a 0 for these types of particles. So now it's time to make some ionic compounds. And in order to make an ionic compound, it's all about balancing the charges. Because when the cations and the anions come together, they need to combine in a ratio in which there are no charges left over. There needs to be all the positives and all the negatives canceled out. And I'm going to take you through a couple of examples here and show you a trick that will work almost every time. Now, let's first take a look at sodium and fluorine. Sodium's a 1 plus and fluorine is a 1 minus, and this is pretty easy because you just take one of each and you smush them together and you get NaF as your ionic compound. Because if you take 1 plus charge and 1 minus 1 charge, or 1 minus, they add up to equal 0. So it's just one of each. The ratio is a 1-to-1 ratio. Now this next one, though, is not a 1-to-1 ratio. We have 2 positives and only 1 negative 1 charge ion. And so really, when we want to put these together, we need 2 negative charge ions for every 1 2 positive charge ion. So when we write the formula, we say CaCl2, and we use a little subscript here to show that there are 2 chlorine ions for every 1 calcium ion. You simply just look at the charges and figure out how many of each you need of these ions in order to ensure that you have no charges left over. It's all about balancing charges, as I said here on the top. In this next one, I have lithium, which is 1 plus, and oxygen, which is 2 minus. Now this time, I need to double the cation because I have more negative charge than I do positive charge, and so I need 2 of the 1 pluses to equal 1 of the 2 minuses. So when I write this, it's Li2O. Next, I have aluminum, which is 3 plus, and bromine, which is 1 minus. So I need 3 times these. When I write the formula, it's AlBr3. Now, if you take a close look, what I'm doing here is finding a lowest common multiple between the charges, 2 and 1. The lowest common multiple between 2 and 1 is 2. And what you can do, actually, is a little trick. You can take the charge of the cation and make it the subscript of the anion and use crisscross. This is what is known as the crisscross method, and it works almost every time. Just simply take the charge of one and put it as the subscript of the other, crisscross, and you've got the right formula. It works here too, right? 1 plus and 2 minus. The 1 goes down here. The 2 goes down here. So you have Li2O1. Same here. Aluminum is a 3 plus, bromine's a 1 minus. So you put the 3 down here behind the bromine and the 1 down here behind the aluminum, AlBr3. So let's apply the crisscross method to find the formula for this next one. 3 goes down here, and the 2 goes down here on the aluminum. So what you get is Al2O3 because you crisscross. 2 for aluminum, 3 for oxygen, Al2O3. So what I'm saying here is that I have 2 times 3 plus, which is 6 plus on the left, and 3 times 2 minus, which is 6 minus on the right, plus 6 minus 6 cancel out to be 0. This last one, using the crisscross method, we put a 1 down here and a 3 down here, and you get Na3N1. And that is how you create ionic compounds once you know the charges. And you'd be expected to know how to do something like this in the future. Well, that takes care of this video lesson in ionic bonding and ionic compounds. Thanks for watching.